So far we have dealt with the fact that when we go into a magnet, there's an equilibrium nuclear magnetization that develops. We have discussed on how we can get this magnetization into the transverse plane. Now, we know Boltzmann rules. Boltzmann is always right. So we know after we have applied our AB1 field, we've tipped the magnetization in the transverse plane. It's not going to stay there forever. It will eventually at some point return to the equilibrium magnetization. And this return to equilibrium magnetization is what I will discuss in this section. So let's talk about, we have thermodynamic equilibrium. So we have a magnetization, equilibrium magnetization along Z. We'll apply now a B1 field in this on this magnetization. This is done by RF pulses or pulse or multiple RF pulses mediated by the RF field B1. So now we look at the situation. So what happens after excitation? Here's the B1. After excitation, our magnetization is in the transverse plane. This is for a excitation, a 90-degree pulse. Now in this situation, as you've noticed here, we have no longer a Z magnetization. The magnetization is no longer present, and we have a transverse magnetization. So now what happens after this excitation? We know that the transverse component has to disappear and a longitudinal component has to build up. And this is described by a process that's called relaxation. And there are two time constants that are affiliated with it that we will discuss shortly. The transverse component decays and the longitudinal component builds up again along Z to give us the equilibrium magnetization. And this process of relaxation, the re-establishment of thermodynamic equilibrium magnetization, has a phenomenological description. For the transverse magnetization, we'll consider here X and Y axis, and we'll now look at on resonance, that is, we are rotating with the Larmor frequency of the magnetization. We have the change in magnetization is proportional to the magnetization itself. Same for the Y magnetization. And these two expressions are actually fairly similar to what we've had for the linear attenuation coefficient. So we have the same mathematical solution here as we have dealt there, and we are getting an exponential decay of the transverse magnetization. So our transverse magnetization, this is the solution of these equations. Now I'll write here xy instead of each individual component. This just means any transverse component is given by the transverse magnetization at time 0 times e to the minus t over t2. So that this is phenomenological. T2, there are a lot of calculations on trying to tease out from the theory how this T2 is being calculated. For us, it suffices to have to accept this as a phenomenological constant. I will, in the following, give you a rationale what influences this decay time T2. So, what are the mechanisms of relaxation? And essentially what we're dealing with here is the fact that our molecules are not static, that they move. And we have, for example, Brownian motion. Now, if you have a molecule that moves, the motion in a magnetic field will create local oscillating or fluctuating magnetic fields. They are small. You can easily picture this. Here's a molecule that kind of tumbles here. We have a magnetic field, and we can certainly envisage that this molecule on a local level, on an atomic level or molecular level, has a non-constant magnetic field. There are some perturbations to the main magnetic field that are time dependent. So one gets, in addition to the B0, which is on the order of Teslas, one gets a small fluctuating magnetic field. It is small, but it's randomly fluctuating, that is acting on the nucleus. This field depends on the orientation of the molecule, and also how it behaves is described by the correlation time tau c. The correlation time is defined as the time for a molecule to rotate by about 1 radian. It essentially is a way also to say it is a measure of how long the motion between two molecules, for example, is correlated. Now, what are some sources of this fluctuating magnetic field? We have coupling between dipoles of the nucleus of interest and the solvent. So if we take, for example, glucose in water, then the glucose molecule will interact with the water. Here's our nucleus of interest, and in blue is the solvent. Or we have interactions between nuclear magnetic dipoles. That's another source of this local fluctuating magnetic field. So if you have a water molecule and another water molecule, the two dipoles which are not perfectly aligned, they will interact and create this local magnetic field. It is useful here to consider the correlation function, which is given by this correlation time. The correlation function is e to the minus t over tau c, and this function essentially describes the correlation of motion that is t seconds apart. So it's dependent on this correlation time, and what I'm getting at here is the parameter is the correlation time, because that correlation time depends on a number of things that we know. One, on the viscosity. So this is easily envisageable. If you take a sugar molecule in our blood, this sugar molecule will tumble fairly fast, so the correlation time is short. If you take the same sugar molecule in honey, honey has a very high viscosity, so there that sugar molecule will move less. So the correlation time will be longer. Then it makes also sense that as the temperature decreases, the correlation time increases, because essentially at 0 Kelvin we're frozen, we don't move at all. So, and finally, that it is somehow dependent on the radius of the molecule makes also sense. It takes just much more thermal energy to rotate a big macromolecule as compared to a small glucose molecule. So this correlation time has some molecular effects in there, some properties of the molecule itself. So relaxation has in large part to do with microscopic motion, random motion that generates a randomly varying magnetic field, and this has a lot to do with molecular properties of the molecules. So now, how does a locally varying magnetic field that fluctuates cause a loss of transverse magnetization? We will deal with T2 largely as a phenomenological time constant, but in this little example I want to give you some rationalization on how this T2, this decay time for the transverse magnetization, how that is influenced by molecular events. First, to give us an idea what we're talking about, the T2 ranges from typically on the order of microseconds, 10 microseconds in bone, to several seconds in water. T2 is also called the transverse relaxation, T2 relaxation. The underlying cause is molecular dynamics and spin-spin interactions. So if you have nearby spins, and depending on how the molecule moves, this will influence this the magnitude of this relaxation constant. It has also been caused historically spin-spin relaxation because it is based to a large extent on interactions between spins. And this leads to a loss of signal in the XY plane. It's also called memory relaxation. How does this lead to this loss in magnetization that we phenomenologically describe by exponential decay? So let's look at the situation after excitation. We have the transverse magnetization. We have flipped it around X with a B1 field. We've tipped the magnetization along Y. If now you consider your voxel as composed of little subvoxels, and in each of the subvoxels, your magnetic field that the nuclear spins experience is identical for all the nuclear subvoxels, nothing of interest will happen. They will all precess with the same Larmor frequency, and this magnetization vector is preserved. But now we have random local magnetic fields. Take your voxel and imagine that you've cut it into tens of thousands subvoxels, tiny little pockets where in each of the pocket you have a magnetization, a tiny magnetization associated with it. So subvoxels, if you will. Now it's assigned to each, in your mind, assigned to each of these subvoxels a slightly different external magnetic field B0. So now what you will get is that in your voxel, these magnetizations will now precess at different Larmor, slightly different Larmor frequencies. And if they have slightly different Larmor frequencies, even if we put ourselves into the rotating reference frame of the main Larmor frequency, some of them will precess faster and some of them will precess slower in that rotating reference frame. If they don't precess exactly at the same frequency, that means between these magnetizations an angle will build up, and this is in this looping animation here, that we have this build-up of the angle between the magnetizations that produces the dephasing of the spins, and therefore a reduction in, as they lose the same orientation, the effective magnetization, transverse magnetization that we measure is reduced. So we have a rule of thumb for water, and that means the less the water is in contact with tissue, be it bone, be it membranes, be it proteins, etc., the longer is the bulk water T2. So the purer the water, the longer is the T2. The longest T2 that you can have for water is degassed, demineralized water. How does this T2 relate to the correlation time? So any of these things increases the correlation time of water. If we look over a voxel, we have the density of our spins times the local fluctuation in the magnetic field with time times the correlation time. And so if our correlation time increases, then this term here increases over tau c, and so we get a faster differential precession, a longer differential precession until the molecules reorient, and this goes to zero faster. So, and here's another major conclusion. If your object of interest, your molecule of interest, has a long correlation time, it accrues a large phase difference over this correlation time, and this results in a short T2. That is important, and the conclusion is this one. This is the take-home message here. Bone, membranes, proteins, for intents and purposes of biomedical imaging, they are invisible. That means, although they carry magnetization, it decays so fast that we cannot practically measure it. So here's an example. We have the transverse magnetization. In cerebrospinal fluid of the brain, there is hardly any proteins. This decays the slowest. The T2 is 1.4 seconds. We have gray matter. It's 100 milliseconds. 90 milliseconds is white matter. And fat, for other reasons, has an even shorter T2. These are some examples here for the relaxation that they are, because of the differential environment and the interactions that the water molecule has on a molecular level. These interactions are different for different tissues, and that is a source for changes in T2 between different tissues. Now, we have said for relaxation to occur and for the thermodynamic equilibrium magnetization to be re-established, we have to re-establish the magnetization along Z to get to the equilibrium magnetization. And so there is also something happening with the longitudinal magnetization, the magnetization along Z. So we consider that we have excited our magnetization to the transverse plane. The transverse magnetization MXY has decayed by T2. And now our Z magnetization, which is 0, has to be reconstituted and approach the equilibrium magnetization. And this is described by the longitudinal relaxation, which happens along the Z-axis, and this is governed by this differential equation here. So we have the time derivative of the Z magnetization component is given by something minus the Z magnetization times a constant. So if we have the derivative of something equals to something of that derivative and a constant, it makes sense to consider an exponential solution here as well. So let's first, however, look at what happens after T2 relaxation. We have no Z magnetization, so it is 0. And the solution to this equation here is given by this solution here. You can verify by plugging this term in here doing the derivation that this is indeed the solution. If we set t equals 0, then we have mz of 0 equals mz of 0, so that works. If we set t to infinity, t over t1, this goes to 0, this goes to 0, then we have m0, so it's the right behavior. So what this means is that after we have had T2 relaxation, we have no magnetization, nuclear magnetization in our sample, and as T1 relaxation, this equation here on the left works, the Z magnetization is reconstituted until the equilibrium Z magnetization. Now, what are the mechanisms for T1 relaxation? They are, again, have a lot to do with molecular motion, its incoherent fluctuations, and it has to do a lot with how these fluctuations, the motion, the molecular fluctuations are close to the Larmor frequency. Remember, a change in thermodynamic equilibrium magnetization is associated with a change in energy transfer between the energy levels in a higher and lower energy diagram. It has therefore been also historically called spin lattice relaxation because one can consider the spin pool as a thermally isolated pool and the heat is lost to the surroundings. Remember, if we have a 90-degree pulse, we have equal distribution of the spins in upper and lower energy level. This corresponds technically to a temperature of infinity, so the spin system has to cool down. Incidentally, this, by the way, has been used, manipulations of nuclear magnetization has been used at very low temperature to further cool a sample by working with heat and exchange between the lattice and the spin system. To give you an idea what the T1 is, it's typically between 0.5 and 5 seconds. The longest is for water, the 5 seconds value, that's pure degassed, demineralized water. So we have at time after 90-degree magnetization, we have no Z magnetization. So the population distribution is equal in the two energy levels, and this corresponds to a temperature of infinity. So we'll draw the two energy levels here, the lower and higher energy level. Here's our energy difference governed here, and this would be at 0 Kelvin. We have them all in the lower energy state, and we'll take here an extreme drawing here. That is our equilibrium magnetization that we have at the beginning. We start out with equilibrium magnetization, and when we do a 90-degree flip, we have equal population in the higher and lower energy level, which corresponds to infinite temperature. Now we wait, T1 relaxation is happening, and the spins that are in excess in the higher energy level eventually return back to the lower energy level until the Boltzmann distribution is re-established, and then we have thermodynamic equilibrium magnetization, which is dictated by the Boltzmann distribution here. N1 over A2 is equals to e to the minus delta E over kT. Now this change in energy level, the spins that are in the higher energy level, that are in excess, they have to go to the lower energy level. In doing so, they have to give off energy. And this is essentially done by transfer of energy from the spins to the system. And the system here is the lattice. It is done by photon transfer, but it is done thermally. So this energy transfer is most efficient if the motion of the system, that is, the frequency with which the system fluctuates, the energy fluctuates, matches the energy difference here between the energy levels. We want to give off a quantum of photon. We can only give it off the energy in form of exactly this energy difference. And this happens most effectively if the motion has that frequency in it as well. If the motion of the molecule does not correspond to the frequency of, largely does not correspond to the frequency of energy difference here, this delta E here, then where do the photons go? They cannot be easily given off. That's the intuitive description here. So this basically means that the Larmor frequency times the correlation time should be roughly 1. Then we have the most efficient transfer. A most efficient transfer means that we have a minimal T1 relaxation time. Now, if we have solid state like bone or plastics or cement or anything, or teeth, then the correlation time is very long, and the omega tau c is much larger than 1, and then we have a T1 on the order of seconds to minutes. If you take water and you freeze it down to a few Kelvin of temperature, you measure the T1 of in that situation. That T1 is in the order of tens of thousands of seconds. So it's very long because there is no motion close to the Larmor frequency of our magnetization. To sum up here the relaxation of T1, there's also a rule of thumb that is useful for us to know, and it is very similar to what we had for T2. Basically means the purer the T2, the purer the water is, so there's less other molecules that the water interacts, the longer is the T1. The more there are like membranes, proteins, etc., with which the bulk water can come in contact, the shorter is the T1. That's the rule of thumb for tissue that is useful to remember.